Have you ever stopped and wondered what's actually going on inside your phone, or your car, or your laptop? It's definitely not magic, but it is this hidden world of teeny tiny components, and every single one has a critical job to do. So today, we're going to peek under the hood of our tech and reveal the secret orchestra of parts that power our world. Let's meet the players. So let me just start by asking you a question. Think about your smartphone, your car, and, I don't know, your coffee maker. I mean, on the surface, they do completely different things, right? One's high-tech, one's low-tech. But if we could shrink down and take a look inside, we'd find out they all share the exact same fundamental secret. And here's the secret. Every single one of them is like its own little ecosystem. It's a really complex system built from this huge cast of tiny electronic parts, all working together perfectly in sync. So in this explainer, we're going to meet the key players in this orchestra, and we're going to start with its conductor.
To really get how any device works, you have to start at the top, at its control center. You can think of it as the brain of the whole operation, the part that's calling all the shots.
And in our devices, that brain is the microcontroller, or what everybody calls an MCU. Now, this isn't just a simple processor. It's basically a whole tiny computer on one single chip. This little self-contained system is in charge of running the entire show, whether that's figuring out your GPS route or just making sure your toast is perfectly golden brown.
So let's break that down a bit. Inside this one little chip, you've got the CPU, which is doing all the thinking. You've got RAM, which is its short-term memory for whatever it's working on right now. You've got program memory, like flash, which holds all the basic instructions. And, this is super important, you've got input and output peripherals, which are kind of like its senses and its voice, letting it talk to all the other components.
Okay, so the brain makes the decisions, but how does it actually do anything? A decision doesn't mean much if you can't act on it. It needs a way to control everything. It needs muscles.
And that's where maybe the most common component in all of electronics comes in, the transistor. Specifically, a type called the MOSFET. Your phone's processor has billions of them. They're so small you could fit millions on the head of a pin. And what are they? Well, they're just microscopic, incredibly fast switches that turn electricity on or off based on what the MCU tells them to do. And by combining these simple on and off states, they create the entire complex language of digital technology. So how does that even work? Well, it can get pretty complicated, but I found this amazing, simple analogy for it on Reddit. Just think of it like a switch that you flip using static electricity. A tiny little charge on one part, they call it the gate, controls a much bigger flow of electricity through the other two parts. There are no moving pieces, it's just physics doing its thing at mind-blowing speeds. Now, okay, this chart looks a little technical, I know, but MOSFETs come in two main flavors, N-channel and P-channel. And all you really need to know is that they work as opposites. One turns on with a positive charge, the other with a negative one. So by pairing them together, engineers created something called CMOS logic. It's incredibly energy efficient, and it's pretty much the foundation for almost every modern chip, including that MCU we just talked about. All right, so we've met the brain and the muscles. But any complex system needs a support structure. I'm talking about the parts that aren't smart, but without them, absolutely nothing would work.
And these are the passive components. So if the MCU is the brain and the transistors are the muscles, then you can think of the passive components as the bones and the blood vessels. Their job is to manage the flow of all that electrical energy, keeping it stable and making sure it goes exactly where it needs to. Let's just do a quick rundown. You've got resistors, which act like dams to control the flow of current. Capacitors are like tiny, super fast batteries, storing and releasing energy to smooth everything out. Inductors also store energy, but in magnetic fields, which makes them great for filtering out noise. Diodes, they're basically a one-way street for electricity. And fuses, well, fuses are the bodyguards that sacrifice themselves to protect the whole circuit if there's a power surge.
So, why should you care about any of this? Because without these humble little parts, our devices would be completely unreliable. Your phone's battery would drain like crazy, your Wi-Fi signal would be a mess of static, and one little power spike could just fry the whole thing. They are the invisible foundation holding it all together. So far, everything we've talked about is happening inside the circuit, in this world of pure electricity. But the whole point of our gadgets is for them to interact with us, right? Out here in the real, physical world. So, how do they bridge that gap? Well, that is the job of electromechanical components. And their function is right there in the name. They turn these silent electrical signals into actual, real-world action. They're the critical translators connecting the digital world inside the chip to the physical world of light, sound, and motion that we all experience.
And these things are absolutely everywhere. They're in the motors that let a factory robot move with incredible precision, they're in the complex systems inside medical devices, and they're in that little motor in your phone that makes it vibrate. They are literally what makes our technology do things.
Let's think about it in really simple terms. Your phone gets a notification. An electrical current goes to a tiny motor which spins a little off-center weight, and that creates the vibration you feel. A device is charging, a signal goes to an LED, which turns electricity directly into light. And you know that satisfying click you hear when a big appliance turns on? That's a relay, a tiny electrical signal flipping a much bigger heavy-duty switch.
Okay, we have met the conductor, the musicians, and even the support staff. So now, it's time to bring them all together for the big finale.
And that performance takes place on the printed circuit board, or PCB. You know that green board you see inside any gadget? Well, that's the stage. It's an incredibly complex network of tiny copper highways that physically holds every component and, more importantly, connects them all so they can talk to each other and work together.
So let's put the whole symphony together step by step. First, the MCU, our brain, sends out a command. Second, that command zips over to the MOSFETs, our microscopic muscles, telling them which switches to flip. Third, all along the way, the passive components, our foundation, are making sure that signal is clean and stable. And fourth, that signal finally reaches an electromechanical part, which creates a physical output that we can see or hear or feel.
From that simple command to a real, tangible action, this all happens in fractions of a second. It's a silent, unbelievably complex and perfectly coordinated symphony of parts. And it's happening billions of times a second, right now, in the very device you're using to watch this.
Which really just leaves us with one final thought. As all these components get smaller and faster and even more integrated, the complexity and the beauty of these internal symphonies is only going to grow. And it just makes you wonder, what amazing new things will the symphonies of the future make possible?